Hello everyone, welcome back to channel. In this video, we'll be discussing about the last problem of today's biweekly contest, maximum number of robots within a budget. The problem states that you are given n robots. Robots has two properties, charge time and running cost. Charge time, like we are given charge time of each of the robots, we are given running cost of each of the robot. Now we are also given a number budget. Now, total cost of running K robots at a time is the maximum of charge time of those robots. Let's say you pick robot number 1, 2, 3. So maximum of charge time of robot number 1, 2, 3 plus you are picking three robots, right? So three into sum of running cost of 1, 2, 3, basically 2 plus 1 plus 3. So this will be the total cost of running K robots. Now, what you need to do or what you need to return is the maximum number of consecutive robots you can run such that the total cost does not exceed budget. So basically, you have to find out how many consecutive robots you can run so that the total cost doesn't exceed the given integer budget. So for example, in this case, if we run first three robots, uh, the cost would be maximum of charge time, which is 6, sum of running cost, which is again 6, into 3, because we are running 3 robots. So 6 into 3, 18, plus 6, 24. So maximum, the cost is 24. So we can, which is less than 25, the given budget. So we can run 3 consecutive robots. Now we will try for 4 consecutive robots. And we will try all possible 4 consecutive. This is one possible way of running 4 consecutive robots. This is another possible way of running 4 consecutive robots. And if that is also satisfied, then we will try 5 consecutive robots. Basically, we will keep on trying the k. We will keep on increasing the number of the value k, and we need to return the maximum value of k that is possible. So hope the problem statement is clear. Now, how to solve this? First of all, let's see that this is the charge, this is the cost function, right? Maximum of charge times and into plus k into sum of running cost. Now, what will be the brute force approach? The brute force approach would be to try every possible combinations, right? So what is every possible combination? You will start with robot one, okay? This is the starting point. Now, what you will do, you will try one consecutive. So you will say that, okay, it is, if is it possible or not? Then you will try two consecutive. You will say, okay, is it possible to run these two robots or not? Then you will try three consecutive, and then four consecutive, and so on and so forth. Now, as soon as you hit that, okay, you are not, let's say you are not able to try, not able to run this four consecutive, you will stop and update your answer to be three, because from starting from one, you get maximum of three consecutive robots to run at a time. So now again you will do the same trick for second index, and for second index again you will try one consecutive robots, then two, then three, and then four, right? So whatever maximum you will get, you will update it for starting index 2 as well. So you will keep on doing this for everyone, and finally whatever is your maximum answer, you will return that. Now, what will be the time complexity of this approach? First of all, you are doing something for each of the index. So what are you doing for each, like you're doing something for each of the index. So there are total n index, and what you are doing for each of the index, you are iterating over each of these, right? So you are iterating over all the subarray starting from that particular index. So in a way, you are incurring extra n cost. So the complexity would be order n square. Now, definitely this will not pass because n is greater than 10 to the power 5. So what we can do? We can't avoid this, right? If we try to do something for each of this index, we actually can't avoid this n. So let's try to optimize this n. What this n denotes? This n denotes that you have to find out what is the maximum index that you can get starting from a particular index, right? So notice that what we have, like we are doing initially. So what we are doing, we start with this, and then we try this, and then we try this, and so on and so forth. So in a way, we are doing linear search, right? And now what we are saying that we have to improve linear search. So the very obvious thing could be, let's see if binary search is applicable here or not. So just to give you an idea, like binary search is applicable if at any index, if something is true and you can decide either to go left or to go right. Basically, based on some condition, if you are able to decide that I can skip half of the elements, then you can apply binary search in that particular situation. So let's see if we can apply the binary search here or not. So what we need to do is we need to find the end index. Let's say starting index is this. We need to find the ending index, right? So now what would be the ending index start if the starting index is this? So let's say the ending index is this. Just assume. Now if this is the ending index, now can you say that if this index is valid, let's say this subarray is valid, then can you say that you can skip all the subarray that is before this? You can, right? Because if subarray of size 3 is valid, then subarray of size 1 and subarray of size 2 with the same starting index would be valid as well, because charge, like sum will be increasing, so there is no point in discussing sum. This also will increase, so there is no point discussing this. Now this charge time is something that also will increase. So basically you are taking more elements. So if you are taking more elements, the chances of maximum becoming more is increasing. So in a way everything is increasing. So this entire thing, if it is true for 3 length array, it will be true for 2 length as well as 1 length array. So now in a way what you are saying that if I am at index I, and everything starting from start index, sorry, if everything starting from start index up till I is valid, then I can skip entire left half of the array and only search in the right half, right? And that would actually decrease the time complexity of searching from n to log n. Now there is one more thing to take care here, is that you need to compute this cost function, right? Because that's your deciding factor. Now notice that you have to find the sum of running cost. So sum would be easy, you can just do prefix sum and you will get the sum. But what about max? So max, actually you have to find maximum in a particular range, right? So if you are considering this range, let's say starting index is this and ending index is this, so like from static to I you have to find the maximum value. So this is a range query, range maximum query, and you can do it with that was segment tree easily, right? Or any other range minimum data structure, because the array is constant. So now what for calculating like what you are doing, so the total log n iterations will be required, right? Because you're doing binary search, so log n iterations would be required. In each iteration you will be calculating the cost, right? And what, like for calculating the cost, this is constant, this is order one time, you can calculate this in order one time, right? And this k is also constant, so this is also order one. Now for calculating the charge time, you require order log n time, right? Because for calculating the charge time you will be using segmentary or something like that. So like the fastest way is that you can do it in order log n. Now this charge function, calculating this charge function once takes order log n time, and you have to calculate this charge function total log n number of times. So what would be the total time complexity uh, of finding, like of running one binary search? It will be log n into log n, right? Log n is because the first log n is because you are running binary search, so you will be actually hitting log n number of i's, right? And second log n is because in each iteration, let's say you fix some I. Now whether like to decide whether to go left or right, you have to calculate this cost function, and this cost function calculation itself requires log n time because of this expression max of charge times. So in total, a single binary search would require you order log n into log n time, and in total you have to do this for every index. So basically we have fixed our start index, right? Now you have to do it for every index. So there are n indexes, and now this is the entire time complexity, order n log n square. So this can pass or cannot pass depending on how you implement it. We will look at the solution, one possible implementation of this particular solution. But as mentioned, we can do better. We can remove this login factor as well. How we'll look at, but you can definitely implement this, and this is definitely a lot faster than order n square, right? So what we have done, we have just started with a brute force approach, and we have seen that we are doing linear search, and we have converted a linear search to a binary search because that's what uh, that comes to your mind when you are doing linear search and you have to optimize it. Now, once you apply the binary search, you see that you can remove this n and bring a login here. But now you to calculate the charge times, you have to incur extra login cost. So in all, you ended up in a solution of order n login square. So let's just quickly look at the pseudocode for this. So pseudocode would be looking something similar to this. So what we are doing is, for each start index, we are doing a binary search and finding the maximum ending index. And where we are doing binary search, starting from this start index up till n minus 1. Now for each index m, because we are doing binary search, right? So we will be evaluating something for the middle index. So for each index m, we are finding out the max of charge times, which can be done through segmentary or any other range square data structure. And then you are finding this the second expression of this cost function, which is k. The k is you are ending here. So what is k? K is difference between start and I. So this is the k, and then you have calculated sum. You can calculate the sum using prefix sum. So this is the cost function, and based on that, you will either go left or right, and finally you will get a maximum ending position. And you can just like what you can do, you can just say that, okay, my result, sorry, so what you can say here is result equals to maximum of result comma maximum index, maximum end minus start index plus 1, right? So basically you have started, like we have started from this start index, and this is the maximum ending index that you can go that you get from binary search. So this is the maximum consecutive robots that you can run starting from start index. So you will do this for every start index, and finally you get the answer. So we'll look at the implementation for this now. Okay, let's look at the implementation first, and then we can look at this, or let's look at the solution. Okay, so another solution for this is using, like basically we already had a solution that works in order n log square n, right? We already have a solution for this. Now what we need to optimize this. Now to optimize this, remember how we get here. We get here by saying that we will do something for every index, and if we are doing something for every index, we are requiring login into login time. That is for sure, right? We actually can't optimize this if we are doing something for every index, because that's the worst you can do. We have seen that there are two expressions, and calculating this expression is not that straightforward because it requires maximum across a range. So we can't actually do better than this if we are, like if we are applying binary search for every index. So in a way we don't have to apply binary search at all for every index, because here we are applying a binary search for every index, so we can't do better than this. So we have to avoid binary searching for every index. Now what instead we can do, what we like in every such scenario where some we have to do something across k indexes, we can do binaries, we can try doing binary search for k itself. Basically what we are saying that for k consecutive elements, whether something is true or not. So we have already seen that binary search property is beautifully applicable here. That is, like if let's say a k is possible, right? Then we don't need to check for k minus 1 or k minus 2, and so on and so forth, right? We don't need to check for any of those. Instead we can, what we can say that, okay, if k is applicable, all of this would be valid as well, and we can directly move to the right, right? So we have already seen this property, and this property applies here. Now we can actually do binary search on k itself. Now what how we can do that? So basically we are fixing how many indexes, like, or how many consecutive indexes are there which we can try. So first of, let's say k equals to 3. So if k equals to 3, what we are saying that whether k equal to 3 is possible or not. That's it. If k equal to 3 is possible, we will not try 1 or 2, we will just try after 3. If k equal to 3 is not possible, we will not try anything after 3, we will shift our right index to the to before of k. So let's see this in action. So if k equals to 3, in a way, what we need to do, we need to try these, like this combination, this first, this second, and this third, and see if any one of them is valid or not. So now let's say you are trying this like your, let's say you are trying these combinations. How many combinations are there? First of all, there are total, in worst case there can be total n different combinations, right? Now for each combination again you have to calculate this thing, right? So how can you calculate this thing? This sum again can be calculated using prefix sum, so there is no issue with that. K is constant, so that's fine. Now maximum of charge time, again you have to calculate charge time across a range. So if we do binary search again, there is no point. But instead of doing binary search, there is something unique here. uh, we have to find maximum in uh, in a set of three. Basically, consecutive set of three, we have to find maximum. So this property that we are finding maximum in consecutive set of three is something that we can utilize and optimize the time complexity, or basically we can skip using segment tree at all in the first place, and instead we can what we can do, we can use DQ, like double-ended queue, to calculate the maximum in a range of k elements. So this is again a standard problem. If you haven't done this before, I would encourage you to do it before actually implementing the solution for this problem. But if you have done it before, I hope you get what we have to do. Basically we have to find out the maximum in a range of k consecutive elements to get this particular value. And sorry, so to get this particular value, and finding out maximum in the range of k actually takes overall order n time. So basically for every k bucket, you can able to find out maximum in order n time. So n number of buckets, and in total you are requiring order n time. So this is what you will be requiring for finding out whether a particular k is valid or not. Now, how many such k you will try? Because you are doing binary search, you will only try log n number of k's, right? So, in a way, now your complexity is reduced to order n log n. So, hope this makes sense. So, let's look at the pseudocode that would make things a bit more clear. So, what we are doing, we are binary searching on k itself, right? And what each k denotes, each, let's say we are searching for k equals to 3, so it will denote from 0 to 2, and then from basically we have to check for each of these group. And if any of these group, if for any of these group this cost function is satisfied, that is this cost function is less than or equals to budget, then we can say that our objective is satisfied, and we can return, like this k is something which is possible, so we will try for everything on the right. Otherwise we will try for everything on the left, right? So now for doing binaries, like what we have to do, we have to find the cost function for each of these groups. Now how to find cost function for a single group? For a single group we have to find the maximum charge time from group start to group end, and sum of running cost from group start to group end. So this sum of running cost is something that is possible using prefix sum in order one time, and maximum charge time is something that we have said that we will use doubly indexed queue, and across all the groups, like not just one group, across all the groups, we can calculate this value for all the groups in order and time. So order and time across all the groups for this, and order one time for each of these groups. So in total, order two and time for calculating this entire thing. And if any one of them is true, we will get the decision whether to go left or right. And we have to do this for log n number of k's because we are binary searching on k, and hence the complexity is order and log n. So hope this solution makes sense. Let's look at the code to. So basically, I have written a class for running max k so that the people who don't understand doubly ended queue to find out the maximum in a range of k, they can also understand the problem. I will encourage for them like who don't understand WNZ queue. I will encourage you to copy paste this structure and try to implement the rest of the code yourself. Uh, Otherwise, you can implement the entire code with this structure as well. So what we have done, as said, we will calculate the prefix sum. Now we will do a binary search for k. So this is the binary search logic. Now we are trying like k, we are finding the middle, and this is our k, right? Now this is the function which will check whether one particular k is possible or not. So if k equals to 0, then it is always possible. Basically, there is nothing in the group, so it is possible. Now otherwise, we have defined our running max k. This will take order and time over the entire k groups. And we have also defined these. Now we are iterating over every groups. So for each group, we are finding out the cost function, and this cost function is something this structure is giving us. Basically, we have a function called maximum, which will give us the maximum of current bucket. And if we do next, it will do something, and if we call maximum again, it will give us the maximum of the second bucket, and so on and so forth. So what we are doing, we are finding out the cost function for this particular bucket. If this cost function satisfied the budget, we data return true. Otherwise, we are incrementing our bucket. Basically, we are saying that whatever algorithm is written here, we are saying that increment it to the next bucket, and then we are again finding out this thing for the next bucket. If any of these bucket is satisfies the budget, we will return true. Otherwise, we will return false. And based on that, we will decide whether to go left or right. So hope this entire solution is clear. If you have any doubts in the problem, please post them in the comment section below. I will also post the solution using segmentary in the comment section below. Make sure to check it out, and I will see you tomorrow. Thank you.